Welcome to Microsoft Build 2017. My name is Edward Thompson. I'm a program manager at Microsoft on the Visual Studio Team Services team, and I'm going to talk about Git at scale. Some of the ways that you can use Git to manage very large repositories that kind of push the limits of Git, and some of the support in Visual Studio Team Services for these large repositories. When we talk about scaling Git, we talk about scaling Git in one of three ways. First of all, large teams, many developers working in a single repository, pushing to the same branches. We talk about scaling Git to large files, handling large data sets for science or game models. Finally, we talk about large repositories, those that have millions of files over years of history. Each of these have unique concerns that affect how Git handles them. We'll take a look at each one of these. What do we mean when we say supporting large teams in VSTS? Well, we found in the VSTS team that about 200 to 300 developers is really where you start seeing contention pushing to the server, and where all of a sudden there are so many branches on the server that they become uninteresting and they sort of bloat when you try to do a git fetch. When we talk about contention for pushing, what you see is the inability to actually get your changes onto the server. So if I take a look at just a simple repository here, I'm using the Git flow model, and I've got a topic branch that I want to push. Okay? So right now, I can see that I am on my topic branch, and I want to integrate that with my develop branch. That's my integration branch. So I'm going to check that out and merge my branch into it. Then I'm going to push that to the server. Or I'm going to try anyway. Often when you have a large development team, you've got a lot of people pushing to the integration branch all at once. So I may not be able to, and in fact, I can't. So what happens is that the Git server is telling me that I can't push my changes. Somebody else beat me to it. So what I actually need to do is get their changes and integrate them, and then I can push. If you want to look at the graph, you can kind of understand what that means. So here I've got my main integration branch. I'm going to go ahead and pull that down. I'm going to create a topic branch, make a commit on that. And when I want to go push, I discover that somebody else has actually snuck into the integration branch ahead of me. So what I need to do now is either merge that change or rebase my change on top of it, and then I can do the push. Very straightforward. This happens all the time. But when you get to 200 to 300 developers, you'll find that often somebody's beating you often. It turns out that while I'm doing this work, somebody else is also doing the same thing. And so we get caught in this loop of over and over again trying to pull their changes down, merge them with mine, and then push them back up. Okay? This is a really painful cycle, and if we could just reduce the amount of time that this takes, we could eliminate a lot of this contention. And it turns out we can with a technique that you're probably already using, and that's pull requests. You're probably using them for code review, but they do an excellent job reducing the contention, pushing to the server. That's because the merge, when you do a pull request, it occurs all on the server. There's no need to take the time to download the changes that you need to integrate with, to do the merge locally, and then to try to push it back up. They're also updated immediately whenever the target branch changes. So you don't even have to run any commands or type anything. It all happens on the server. The only time that you need to actually do anything manually is if there are conflicts. That's when you need to download the latest code from the server, integrate it with your own, resolve the conflicts, and then you can do the push. Okay? So pull requests, it turns out, are a really excellent way to make sure that the server is integrating your changes for you, that you're not doing it manually. And you can actually enforce that everybody's using pull requests to do this by turning on a branch policy. It's not just for code review. So here I have my repository on Visual Studio Team Services. I go to the Branches tab and select my Develop branch and click the More Actions button. I can select branch policies. And then at the bottom of the branch policies page, I can turn on code review requirements. But I'm going to select a minimum number of reviewers to be just one. And I can allow my users to approve their own changes. And when I save that, now anybody can create a pull request and merge it on their own. They don't need a code review. We can turn on code reviews later if we want, but this gives the same effect of being able to push changes directly into the integration branch, but using pull requests, it reduces the contention. Okay. The other common problem we see at about the 200 to 300 user level, where you have that many developers all working in the same repository, is you have uninteresting branches. And when I say that, I mean that when I do a fetch from the server, I'm going to get all the branches that exist, all the data in all of them, right? And that's probably not really what I want. The only ones I care about are the common branches, like my master branch, releases branches, the branches that I've created. I don't necessarily want to see everything that my coworkers have been working on for the last however long. They're great people and I love them, but I don't need to see their code all the time. It just bloat when I do a get fetch. So Visual Studio Team Services is offering a new functionality called limited branches, where you only get to see your favorite branches when you fetch. So you'll get the common branches like master and the releases branches. You'll get all of your branches, but you won't see your coworkers' branches unless you go and explicitly ask for them. So this drastically reduces the amount of data that's being transferred over the network, the amount of time it takes to do a get fetch when you're working on a large team. Limited branches are not yet available. They're coming soon. Pull requests, of course, are already available, and you can find more information on visualstudio.com. Another way we look at scaling is to support large files in Git. Now, if you're just checking in a DLL, some binary once, that's not a problem. But the way Git stores history, it's very problematic if you're storing binary files that you're changing often. That's because when I do a pull from Git, I'm not just getting the most recent commit. I'm also getting all of the commits that have ever been introduced in history and all of the files that go along with that. So even if I'm checking in a reasonably small PNG or image or game model, as I'm changing that over time, I'm bloating the repository. And every time I do that pull, I'm going to get every copy. So the best practice is actually not to check those binary files in. So what you can do is use an extension to Git called Git LFS, or Git Large File Support. And what Git LFS does is it replaces the binary itself in history with a pointer file so that it knows where to find that image when it needs it. So the pointer file is about 128 bytes, much, much smaller than anything that you're replacing it with. So you can get the binaries out of history, replace it with this very small pointer file, and Git LFS will on demand bring the binaries in when it needs it. Okay? Let's take a look. I'm going to clone a repository that has large files in it. And in fact, the files aren't even that big. There's 1 megabyte PNGs. There's only about 10 of them in my current version in head. It's not that big, but I've been changing them throughout time. There are about 750 different revisions of these 1 megabyte pings. That adds up to 750 megabytes. So right now I'm cloning 3/4 of a gigabyte, very slowly. So I'm going to cancel that. Instead, I'm going to clone the same repository that was produced with LFS. So all of these files have been added with Git LFS. And so instead of actually putting the binaries into history, we store the Git LFS pointer files. And you can see that receiving objects took just a second, right? Because all that we downloaded from the repository was the pointer files. And now Git LFS is downloading just the 10 PNGs that make up the current version. Okay. It's going to take a second. It's not instant. Git LFS is actually doing some performance work right now so that this can be parallelized, so that this is much faster. But it's still a lot faster than downloading that 3/4 of a gigabyte was about to be. Okay, we're almost done here. Now, people ask me, why wouldn't you use a shallow clone in this instance? A shallow clone lets you download just the most recent commit from history and the files in it, but it will leave out the rest of history, so you'll get some of the space savings. But unfortunately, what you don't get is the history. So with GitLFS, if I navigate into my repository folder, I can see that I have the files. These are my 10 PNGs, but I can run git log, and I'll also see that I have some history. If I'd done a shallow clone, I would just see the most recent commit. I wouldn't see any of the history. And what's more important is that with a shallow clone, I wouldn't be able to switch branches. With GitLFS, I can switch branches, and when I do, it will page in just the differences. It'll download them from the server, the files that I didn't have in my current branch, and just show me just get the differences. So it's a very efficient way to handle binary storage with Git. You can get more information on GitLFS at github.com/GitLFS. Finally, we want to talk about scaling to large repositories. And by this, I simply mean repositories with a lot of files. A lot of people talk about Git as having been invented to handle large repositories because it was invented to handle the Linux kernel. And the Linux kernel is big. It's got about 60,000 files. But to be honest with you, at Microsoft, that's not what we mean when we talk about large repositories. There's only one repository that we mean, and that's the Windows repository. It's got about 4 million files. It takes 4 million files of source code and build tools to make up the ISO that you get. And you know, the last time you downloaded a Windows ISO, it was not small. So you can imagine that the repository that builds it is also not small. It's about 300 gigabytes. That's 20 years of continuous development history. Windows is checked into a monorepo, which means that it's not split up into submodules. We find that the best practice, the easiest way for our developers to work is to have everybody in the same repository and not split it up with submodules. Especially at Windows scale, submodules really are not effective. And other companies have found similar functionality out of monorepos becoming the best practice. The problem with them is that without extra tooling, they are unbearably slow. When we first put Windows into the Git repository, it took about 12 hours to clone, and it took about 3 hours to switch branches. So if you're using Git, if you want to use the functionality of a distributed version control system and have fast branching and merging, having 3 hours does not cut it. So we've introduced something we call GVFS, which is the Git Virtual File System. The way GVFS works is that it's actually rather similar to GitLFS. It only downloads the data that it needs, and it pages the rest in on demand. When I clone a repository with GVFS, I get the information about the file system structure, but I don't get any of the files. Instead, I run a background process called the GVFS driver. So when I can see this information on my disk, it appears to be on my disk, but it's not actually there until I try to open the file. And when I read the file, then the GVFS driver, which is a file system driver, will download the data from Visual Studio Team Services and put the data actually on disk. So data is only paged in as I read it. And that doesn't sound like such a big win, but it actually is. Since most developers aren't working with all 4 million of those files, they're only working with a tiny fraction of them, it completely changes the dynamics and allows Git to be functional for the Windows repository. Without GVFS, it took 12 hours to clone. Now it takes minutes. And all of our, sort of working with Git functionality, checkout, status, commit, most of them take just a few seconds, and some of them take, up to 30 seconds. So that's really the game changer that allows Windows to use Git. GVFS is currently in heavy research and development. It is in active usage within Microsoft, but it's still in R&D. Right now it's tied to Windows and Visual Studio Team Services, but it is open source, and we're working with the Git community to bring GVFS to a wider audience. You can find out more information about GVFS at aka.ms/GVFS, and you can find out more information about all of the technologies that I've talked about to help scale Git at visualstudio.com. For GitLFS, it's at github.com/GitLFS, and GVFS is at aka.ms/GVFS. Thanks.